Hello everyone, welcome back. Reverse engineering Linux 32-bit applications. So we're going to continue our discussion of stack buffer overflows. We've been talking about these for quite a while now. And I wanted to add a few things. So in a previous video, we had talked about the fact that with Linux, things are complicated. We said Linux does not like to be exploited. So the compiler is going to have a stack protector. Sometimes it's called a canary. So there's some extra things added so that if you tamper with the stack, it's detected. So there's a canary that tells you, hey, this has been detected, sort of like miners. A long time ago, miners, they would have birds in the mines with them. So if there was some sort of toxic gas, the canary would die and they would know there was a problem. So it's very similar to that idea. We also said that there was a problem because the stack is not executable, and that can cause an issue. And furthermore, we said that we randomize our addresses on Linux. So we noticed that the addresses were randomized, and we're using address space loading randomization. And that is a problem for us. So what I wanted to do now is to kind of go through these different issues one at a time and talk about ways that we can try and bypass these issues. So, we have address space layout randomization, which is something that is done by the operating system. We're not going to talk about that one just yet, so I've still disabled that. We have the stack canary, which is also known as the stack protector. We're not going to talk about that in this particular video, but I did want to talk about getting past this problem of a non-executable stack. So we need to get to a place where we can execute some code. Now, one common place that we will go is libc. Why libc? Every program, for the most part, is going to have libc loaded. Certainly if it's a C program, this will be the case. So once again, let me go ahead and load up my program. I'll just run my little testy script. We're not actually going to run it all the way through in this case, but it's a convenient way to launch this. And I will change my shellcode. And for now, I'm going to change my shellcode to just be a few A's. Because again, I have changed this. And I'm not going to try to run the same kind of an exploit. So let me go ahead and run my analysis. And now let me view my different memory regions again. And I notice that I am loading my LD library. Let me go ahead and step through this program, hit my breakpoint, and I want to relook at my different memory regions. And now I also have libc. So why did I want to do that? I wanted to do that because I want to look at libc that is loaded every time. And I want to see if I can find a function in libc that I could somehow call and exploit. So here is my libc. It is loaded into this location. So I'll just make a note of that. F7 E01000. I can also see this by looking at my proc map for this particular process. If I wanted to do this on the command line and outside of my debugger, that's another option. But we won't do that just now. So we're going to start with sort of the easier way to go. I can go ahead and analyze this region. And I can see all of the various functions that it provides. So now what? I want to find the location of a function call. Now I have a couple of choices, but a common choice would be the system function call. So the system function call allows me to execute an external program. So let me go ahead and do that. Now there are a couple of ways that I could try to find this. I could try to search for system. And I can see where that's available in this binary. Now this is kind of the hard way to go, where I'm just searching for this string. And let me show you the easier way to go ahead and find this. So I know where this thing starts in memory. So now I'm going to go ahead and use a different tool in order to find the offset in memory for this. So again, this was loaded from lib32 libc-2.23.so. So that is what I want to search. That's lib32 libc-223s0. And that is the start of this executable. So if I go to my command prompt, And I'm going to run this command. I'm going to run readelf. This will read my elf file. It's an executable and linkable format. It is not an executable Linux file, as some people think that it is. And I will look at lib32, libc 223 so. And this will show me all of the functions that are available in this library, right? And it showed me too much. I didn't want to see all that. So I'm going to pipe this to grep for system. And now you'll notice that at this offset, I have this call to system. So that offset was 3A940. That was my location for system. So if I go back, and I look at my offset of 3A940, here we are. So here's my offset. If I took F7E 0100 and I added to that 3A940, I get F7E3B940, and that is the start of this function. So what is this function? It just so happens to be my system call. So my system call will allow me to execute an external function. So that final address that I want to use is F7E3B940. So this is the address I want to return to. So I'm going to return to a libc address. Now what happens when I do this? Recall that when I call a function that uses cdecal, what's it going to do? It's going to say, oh, well, I will call this function that is at the top of the stack. That's the address. And I am going to pass it parameters that are pushed onto the stack. So what parameters should I give it? What should I be trying to run? Well, a common thing I might try to run is a shell. So I could run a shell sh. I could run a better shell like bash with bash. So how can I do this? Well, I need to have a string. of SH or BASH, whatever. Now, there are a couple of ways that I could get a string like this. One of the ways is I could get lucky. I could find this string somewhere. I could find this string somewhere in my application. So I could do a search for that, and I could find that string sh in my app or in a library. And then I can use that address as my parameter. I could say, hey, here's my parameter. It's sh or bash. Please use that. So that is one way that I can go. But it's not the only way that I can go. So either I push it on the stack myself, or I just find it in my program if I'm really lucky. Okay, so now what? Let's see if we can modify our script in order to redirect to this new address. So our new address is going to be right here. We said it's going to be F7 E3 B9 40. So that'd be 40 B9, and then E3, E3, and F7. And now what do I want? I want to run this sh. So I want to see if I can push this onto my stack and then have that as my parameter. So this is sort of the naive attempt to run system and give it this as a parameter. So I'll say sh, and then I will add a null string to it explicitly. I will exit my Evans debugger, and I will rerun my new script. And of course, it didn't like that I had a null string in there. So naive attempt number one, unsuccessful. So let me go ahead and let's get rid of this null. And we'll see how far we get. I suspect we're not going to get all the way there. Well, of course, let's be honest. I know we're not going to get all the way there. But I want to take some baby steps toward the answer. Let's go ahead and run. Analyze. Once again, go ahead and set a breakpoint. I'm going to set it actually past my buffer overflow in this case. and set it right here. Go ahead and run to the new breakpoint. Move my return value. Now I call leave. Okay, so what do I have here? Here I have on my stack this F7E3B940, which is in fact the address I said I wanted. So this, in theory, should point to my call to system. What else is on the stack? I have SH and then a null and then FF. So this isn't quite what I want. But let's see what happens. I'm going to go ahead and step into this return. And here I am. I am in that system call. I can go ahead and analyze this region. And it says, yep, this is nothing more than a simple function. Here's the start of it. So I'm going to step, I'm going to move. I'm going to call this function. I'm going to step over that. And I'm going to go ahead and step out. And it tells me that I got a signal. So basically, it tried to run a shell, but it didn't do it quite exactly the right way. And that's what led to this issue. You did notice that we successfully redirected our code back into libc, and we're able to call something in libc. So how could I successfully do this? Well, there are a couple of ways that I could go. Now, the easiest would be just to have access to this string in my application. So maybe it's a little bit like cheating, but let's go ahead and change this just slightly. So if I go back to my app, here it is. And I am going to be lucky. And I'm going to create a local variable. I'm going to call this lucky. And I'm going to create the string monster bash. So now what? Now I have this string bash, and I can pass that as a parameter to system. Now, if I'm not sure what the parameters are for system, I can easily get that. How do I get that? I could do a man on system. So now that I've done this, I have to go back to my shell. Let me stop this. Go back to my shell and recompile. Now in this case, I'm going to turn off the executable stack protections. Gave me warnings. Going to rerun it. Run to my breakpoint. Analyze. And I'll set a breakpoint right before leave here. And I'll run to the new breakpoint. Step over this. I have my return value. I call leave. And now I have my new value. And it's going to call return. Before I call return and I get redirected here, what do I want to put on my stack? Instead of having this value of sh on my stack, instead I want to have a pointer to this string. Well, let me have a look right here. I have a pointer to the string monster bash. And that is stored at 8048533. So if I look here, if I look at 8533, I see monster bash. And here I see BASH and then a terminating null. So this is exactly what I want. So that is at location 0804853, and then what? This is F, E, D, C, B. Or if I start here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. So that is the location of bash. Bash is at 0804853B. So that is the location I should be putting right here, assuming that's the only parameter for my program. So once again, I'll go ahead and exit. And you might say, how do I know if that's the case or not? I can do a man on system. And you'll notice that system takes one thing, a string, to run. So there's my string. Let me go ahead and modify my little testy script. And now my shellcode will be this address in little endian format. So backslash x 3b backslash x 85 backslash x 04 backslash x 08. That is my new string. Let me go ahead and run that. So once again, I'll run testy. Run to my breakpoint. Analyze it. Set a new breakpoint. Run to that. I call leave. Here's my address. And what's on the stack? Nothing more than the location of bash. So this is looking pretty promising. So now I can go ahead and step over this. I'm feeling confident here. I'm just going to step right over it. And I'm just going to let it run. Now in this case, it got to the end of the program and it gave me a signal saying, hey, I didn't quite like that. And there were reasons for that, and it has to do with the way that it's being run in the debugger and things like that. Okay, so what's the moral of the story here? How do I get past this protection? Again, I recompiled this. So if I view my different memory regions, notice that the stack is no longer executable. So I need to go somewhere. I need to go to a place that has executable permission. Well, that place could be somewhere in my program. Chances of my program having something nice and juicy that I can exploit somewhat low. I'm not going to say it's zero, but it's not terribly likely. And what about my libraries? Well, libc is going to have all kinds of things. And of course, system is a fun one that you might use. And there are some others as well. So that is a quick introduction to return to libc. This is a way to get around one of the many protections that Linux will put in place for you when you're running an application. And that's all I had for this video. As a reminder, this video is one in a series of comprehensive videos on many InfoSec topics that are available here at Pentester Academy. And I hope to see you in another video from this course or one of our other courses soon. So I will see you then.